This is Module 15 of Engineering Vibrations 1. The learning outcome for today is to express the transient response solution of the differential equation of motion for a simple single degree of freedom system in phase angle form. And so here's where we left off. We found the response solution to this undamped vibratory system with just a spring and a mass. And we defined the natural frequency, and we applied the initial conditions to come up with this response solution. Now we want to, the response solution is in a combination of sines and cosines. So we'd like to look at a different form. We're going to combine the sines and cosines so that we have just an argument where we have an amplitude x times cosine of the omega natural times time minus some phase angle. And that's what we're going to call, again, the phase angle form of the response solution. So there's our response solution in the original form. Here's the phase angle form of the solution. And recall this trigonometric identity from your math days. If you have the argument cosine of some angle A, where A is omega natural t, minus B, which in this case is phi, that's equal to cosine of A times cosine of B plus sine of A, sine of B. And so you can look that trig identity up. And so now we're going to compare coefficients. Okay, so we've got, in this case, Q naught. Here's your cosine omega natural. So Q naught is like the cosine of phi. All right, there's cosine omega natural t, and Q naught is equal to x cosine phi. For the other term, we have sine omega natural t, and here's sine omega natural t. So Q naught dot, the initial velocity over the natural frequency, is the same as x, capital X sine of phi, as we show here. Okay, so we've solved for Q naught equals x cosine phi, and Q naught dot, the initial velocity over omega natural, is capital X sine of phi by comparing coefficients. Now let's square both of those equations and add them. And so we're going to flip sides here. And we've got x cosine phi. If we square that, we've got x squared cosine squared phi. And then we have x sine phi. If we square that, we have x squared sine squared phi. And on the right-hand side, we're going to have q0 squared plus the quantity q dot 0 over omega natural squared. Now, again, a trig identity that you should be familiar with is that sine squared of an angle plus cosine squared of an angle equals 1. And so we then have now solved for the what we call the amplitude of displacement, and it's equal to the square root of the initial displacement squared plus the quantity, the initial velocity, divided by the natural frequency squared. Having found the amplitude of displacement, now let's look at the phase angle. And to find the phase angle, let's take this equation here where we have x sine of phi and divided by x cosine of phi. So there's x sine of phi divided by x cosine of phi. X sine of phi is the q dot naught over omega natural, and x cosine phi is q. So here's the response we get. And we know that sine phi over cosine phi is tangent phi. And so the phase angle then is the inverse tangent of the initial velocity divided by the natural frequency times the initial displacement. We now have the phase angle form of the response solution, since we have the cosine argument here, it cycles between 1 and -1, so the amplitude of that displacement, again, is given the symbol capital X, and the phase angle is the inverse tangent of q dot naught over omega natural times q0. And so I took some actual values of the initial velocity and the initial displacement, and I went ahead and plotted this phase angle form of the solution, and this was what it came out to be. You can see cosine cycles between a maximum of 1 and -1, so the amplitude of that displacement is capital X. Here we have taken the argument of the cosine and solved for t, and so that's where the peak is going to occur when cosine is equal to 0, right? When omega natural t equals phi. And then we have the period of oscillation between two peaks, how long it takes for a cycle to occur. And so for a positive phi, you can see that the first peak occurs after time equals 0. Down here is time equals 0. And we call that a phase lag because the response lags by a certain amount of time. Now, if the response leads, we have a negative phi, and so then the first peak would occur before time equals 0, and we call that a phase lead. So that's a little bit of an interpretation of this transient response. So we call this motion, where it cycles between positive amplitude of displacement and negative amplitude of displacement. It just continues on forever. There's no energy loss because there's no damper. We call this a simple harmonic motion or a simple harmonic oscillator. And so as a summary, we've expressed the transient response solution for the differential equation in phase angle form, and we've plotted it and looked at a little bit of an interpretation of that plot. See you next time.